All right, today we're going to talk about the PCB Blower Control Board. You find these in Amana's, you find these in Goodman's. Long story short, they're used on PSC motors and they're used on ECM motors. So very good boards to familiarize yourself with. We're going to take this to the CANTEX box and show you how to wire it up in practically. Then we're going to put it on a motor and show you how to wire it up practically and talk about all the terminals on this board. A couple of tips so you don't misdiagnose it. We have an integrated fuse, so it's very important. Behind me, we have a timeline. We're going to go over that, and we're going to wire it up on the smart board, wire for wire. So we have different styles of teaching for different ways of learning, and we try to incorporate all that to better help you understand how you can take this and without a schematic, just understand how to wire this up, what everything's for, and why it's there. Stay tuned. Okay, we're at the CANTEX box. We're going to go ahead and talk about the PCB Blower Control Board. You can find these in Amana's. You can find these in Goodman's. We have a CANTEX box with transformers and contactors inside of it with a real live power supply that you can have the same in the field. It's L1 and L2, and we have 24 volts up here between R and C. Our objective is to bring the load on through the blower control board. We do need to get a live 240 volts of electricity between T1 and T2 to get this load to activate. This is just a 120 volt light bulb. I'm going to go ahead and first show you what the CANTEX box power supply looks like on the meter. I'm not going to use the backlight in this, so it should show up. You can leave your comments in the box. Let's see here. We should be showing 27 volts here between R and C. 28 volts there. Between L1 and L2, we have 243 volts. With that, I'm going to go ahead and wire up the load first, not going through the relay on the board. Just to demonstrate, the load does need 240 volts, which is both legs of the power. I'm going to go ahead and take L2 and wire it up to T2. I'm going to go ahead and take L1 and wire it up to T1. And when I touch this, you'll hear the click, which is the contactor inside the box, and the load will come on. And so there's the click. You can see that the light is on. And then if I wanted to break this load, I would come up here through the board. Now there's a common terminal, a normally open, and a normally closed terminal. I'm going to go ahead and wire L1, which is line voltage. Line voltage will always go to your common terminal. We're going to come out of the normally open because we don't want the load to run. I'm going to go ahead and first go to normally closed, just to show you that if I ran power up here, the load will always run. So that's not a good terminal to wire your blower motor to. So we want to come over here to the one on the far left. Now I'm going to go ahead and zoom in a little bit just to help out. Hopefully this is going to help out a little bit. I'm going to go ahead and wire to the left terminal, which will be the normally open. And we're going to wire that up to T1. Now the load's not going to come on because that's a normally open load. So, or excuse me, it's a normally open terminal on a relay. So to get that load to come on, it's going to need a G call. Now, what's interesting about this board is you can see it has an inline fuse. We have to take our transformer and wire to the board, and then through the board it'll go across the fuse and then back out, which I'll explain this. We're going to do this at a blower motor, and we're also going to show you this on the smart board where we go wire by wire. But where you see XFMR, okay, that's going to be where you hook your transformer up to. So you have XF MR-R, and then I have R. So that would be, the first top one would be an input, as long as the fuse is not blown and the fuse is in there. Then R, the one right down below that, which is showing J4 and J1. If you look up here on the top left, I actually have a diagram of that so you can see, so you can follow. But J1 is an output. So that R will be an output to the thermostat. Then we have, below that one, we have C, which is common. And that says XFMR-C. So that, again, that's transformer. So this would be a output path back to the transformer. And then this C down here will be a input from any other commons that I want to use. And as a path through the board, C will be back out to the transformer. And we have our J10 terminal, which is plug. And then we have the J9, which is speed up. And we're going to go over all these. Now up top here, hopefully you can see it, we have M2 and then M1. Those two terminals are park terminals. We'll go over all that. But first, let's go ahead and wire up the transformer. I'm going to go ahead and take R from the top left on our CANTEX box. And I'm just going to wire this to the XFMR-R. And there we have it. So we're already putting 24 volts onto the board. We just need to give it a path back to the transformer. So we're going to skip past the second terminal here, which is R, and we're going to come down to XFMR-C. So I'm going to go ahead and connect to this terminal, and I'm going to run it back up to, I'm going to push my alligator clip little insulation around that just to kind of, I know that's kind of blocking some view there, but I don't want to short 24 volts on my board and blow my fuse. All right, so we're going to go ahead and connect. Excuse me about that. That light will always do that when you first apply 24 volts. It's going to do it again. And as you can see, I'll show you, I can toggle it a million times. That's not wanting to do it for me again, but typically when you first connect it, if you're connecting it with live voltage, the light will come on your load, your fan motor will run for a second. If you're doing this in the lab and using a light bulb, the light will come on for a second. So we have R and C are the only two terminals on this left-hand side of the board right now. And I have to be careful because I'm dealing with live power here, and the last thing I need is to get in a situation where I'm going to hurt myself. So let's go ahead and I'm going to come out of R, which is the middle one. Okay, up here, right above common, that R, this is the output that I would wire my thermostat to. But before I go to my thermostat, maybe I want to go to a float switch. After my float switch, then energize my thermostat. Then after my thermostat, then you know, I would get a G call, and that G call would come down here. So let's just say we went through the float switch, out of the float switch, into the thermostat, and then red energizing G through the thermostat base plate will come back as my G call. So this is going to be where I represent my G call. All right, so I'm going to come down here, and I'm going to go ahead and connect to G, and our normally open portion of the relay will close now in about 6 seconds, and there you have it. And so that's really it. The M2 is a park terminal. M1 is a park terminal. So you have 3 speeds typically on these motors. You have a high speed, a medium speed, and a low speed. Typically, it's recommended that you run everything on a medium speed, so you get 400 CFMs per ton. So the low speed and the high speed that I'm not using, I would just push them on there so they're not just sitting in a cabinet. I want to safe those off. So this board allows me to plug them on the M2 and the M1 spot here on the board, where it's safe. I know where they are. If I need to change speeds, maybe go from a medium speed to a high speed, I can do that. Right now, they normally closed. That's coming up to my T1 to energize my light. That would represent the medium speed tap that I would typically use. So we have this speed up terminal down here. I want to show you what that's for here in just a second. Before I do that, I want to show you the off delay, because it's real easy to misdiagnose these if you have a board that's stuck in the closed position where the relay is just constantly energizing the motor, and you're trying to, you know, make sure that, hey, is my board good? Is my board bad? You know, how would I do that? Well, very simply, if you use a timer, it's the easiest way to do it, because if I use a timer, then I'm not going to misdiagnose it. Even if this has probably been running for 20 minutes, it doesn't matter. I can sit here and come over here and I can release my G call. I'm going to go ahead and do so. And I'm going to hit start. And I'm just going to let this hang. So that's going to represent my G call. And then we can see that in about, I want to say it's 65 to 85 seconds, the load should drop out. And so if I didn't have my timer out, I would probably jump the gun and possibly misdiagnose my board. Also, if you're not getting a G call, you know, you want to make sure that you give it a G call, take the G call away, start your timer, and if you're running, you know, on and on and on for a minute on end, 5 minutes, 10 minutes, you obviously have a bad board. You just need to replace that control board. Get you a new PCB board. There is another board very similar to it. It's called the ICM 277. It looks identical. And then International Comfort, you know, ICM, those products are very similar. You might have a 5-amp fuse on those. Don't be worried if you put a 5-amp fuse in there. I know Goodman's going to recommend a 3-amp fuse. If you have a 3-amp, put a 3-amp in there. If you have a 5, it's not going to hurt anything. It's sitting on a 40 VA transformer anyways. So as you can see there, we ran about the time that I told you. I'm going to go ahead and reset it, and I'm going to show you the on delay now. So I'm going to give it a G call again. I'm going to go ahead and hit start at the same time, and you'll see in about 6 seconds the load will come on. There we go. Now if you do not want a delay, there is a way to bypass the delay. Bypassing the delay, I'm going to go ahead and release my G call. This is going to give it a, you know, pretty much a 65-second countdown. But my J10 and J9, if I short these two out, I will bypass my delay. And that's very easy to do. I'm going to just take another alligator clip and just show you that if I were to jump these two out, just short them out, there will be no delay there. And so I'm going to go ahead and do that one more time. I'm going to go ahead and give it a G call with those two shorted out, and you'll see that my delay will be gone. So there's no delay in the beginning. It instantly came on, and there's no delay when I turn it off. If I lose the G call, we'll do that again. So I can toggle this on and off like a normal relay. Now I'm going to go ahead and engage it again. All right. If I were to remove the speed up, okay, say I'm testing this thing out and I want to see, hey, does this board actually work if I want to give it a delay? Remove your G call, and I don't have my timer out here right now, so we'll just have to assume what 65 seconds, 70 seconds feels like. But this is how you get efficiency in the very beginning. That 7-second delay when the coil is coming on, it's getting either warm or cool, depending on what mode it's in, heat or cool mode. That off delay, it's the same thinking. You're just getting more dehumidification, more comfort out of the back end because that coil is at a higher or a lower temperature than the air moving across it. So why not take advantage of that with the compressor off? So we're just trying to get more efficiency out of the unit, because we are transferring heat still. We are removing moisture at a higher efficiency, because within that 60 seconds, the only thing that's running between the compressor and the blower is the blower. So if you look at what it costs to, every time this thing comes on and off within a year's time, how much more comfort are you giving your home at just the cost of a fan motor running for 60 seconds? If you added that up, that could be 15 cycles a day on and off, 20 cycles a day. That's 20 minutes if each off cycle is 1 minute long. So 20 minutes, you figure up 1 month, 30 days. That's quite a bit. So we can do that math, see what that comes up to. We're going to take that 20 minutes, we're going to multiply it by 30 days. That comes up to 600 minutes. If I divided that by 60 minutes, we get 10 hours. So in 1 month, I can gain 10 hours of cooling capacity without a compressor, all because of this board. And that's why these they say, hey, we're going to get more efficiency if we have an off delay. It's real. You can just do the math. And so that's really neat. Now I want to show you a couple other things too, because there is a integrated fuse on this board. And so if I were to give this back a G call, okay, there's a 7-second on delay because I don't have G and speed up shorted out. Okay, if I were to come up here and just remove my 3 amp fuse, everything shuts down. All right, so these fuses, they can blow, which obviously this one's not blown. You can clearly see it's in contact. However, if you have any kind of power interruption, whether it's power going to the transformer, or low voltage secondary voltage leaving the transformer, or a fuse that's blown, you will, or float switch tripped, anything like that, you will lose the capability of this thing functioning. So if you think that you have a bad board and it has a fuse on it, pull the fuse out, and you can sit there and you can just look at the fuse. Now, if you're still in question, I'm going to show you with my meter. If I were to come over here, I'm going to come over here to my common down here, which is J7. And I'm going to come up to one side where my fuse would be plugged into. And you can see I have 28 volts there. Now, when I go across the other side, you'll see that I have nothing. Okay? And so I don't have anything there. I never recommend you jump these out. I am going to show you that all that fuse does is it closes the circuit from one side to the other. And as long as it's closed, everything would work. You never want to do this. Give it 7 seconds because it has a G call. It'll come on. You never want to do this because if your fuse is blowing, your fuse is blowing for a reason. And anytime you have a fuse that's blown, you want to replace that fuse with the same size fuse. So don't go down to the auto parts store and say, oh, I found a fuse that'll fit, and it winds up being in a 7.5 amp fuse or a 10 amp fuse or a 15 or 20 amp fuse, because you're not going to do anything more than what I'm doing here. So don't do that. You want to just leave it down until you get the right size fuse, and then you want to find out what's causing your short. It doesn't mean that the board's bad. Your short can be anywhere in the low voltage systems. We recommend getting an experienced HVAC company out there to troubleshoot that. So I'm going to go ahead and just disconnect here, which will break the circuit, and you'll see if there's no power coming across where my fuse is at, then it's very simply nothing's going to happen. So we're just going to take the fuse and we're going to put the fuse back in there very carefully here. Okay, a couple seconds, it should come back on. Here we go. And I'm going to go ahead and remove the G-call. We'll just take it off completely. And about 65 seconds, get a little bit of efficiency out of that coil there. It'll shut off on its own. So we're going to take this over to the blower motor, and where I have a couple of other speeds that I can actually plug into M1 and M2. And I'm going to show you there a practical application. You know, we try to do the CANTEX box because it's impractical, but it allows us to focus just on the board, which is pretty neat, because if we're focused just on the board, then we're allowing ourselves to home in on what we're trying to learn and not surround ourselves with all the other components. Even though I can take you to a blower motor and not have the motor inside the air handler, it's still pretty busy, and you'll notice that it's going to be a little bit more necessary for you to have concentration if you're trying to figure out what terminals I'm landing on the board, because you're going to have a noisy blower motor, you're going to have all the other wires involved, and it's going to look a little bit more complex. So stay tuned. We'll take it over there, and hope that helps you out over there, and then we'll take it to the smart board. We're over at the blower motor now. We got a blue light bulb. We got the PCB board. We already have the light hooked up to the board. This is hooked up to the normally closed. This is just to show you that there's always going to be power here if the relay is in the open position for the normally closed, your practical way of wiring the motor. So if the motor's off, there's always power on this terminal. We wanted to demonstrate that so you always know that, so you don't hook something up to it and then wonder what's going on. Run capacitor, we've added a float switch to it so we can interrupt power. Obviously we have our 3-amp fuse that's on the board. We have red, blue, and black. This represents our 3 speeds for common. We use red for common, that's going to be low speed. If we use blue for common, that'll be medium speed. If we use black for common, that'll be high speed. This will represent our other leg, which is wired to our run capacitor and start winding. And we have our power supply down here. We have a live 240 volts and a secondary voltage of 24 volts. I'm going to go ahead and show you here on the meter what our power supply is. You can see here that we are dealing with live power. That is 241 volts. I'm going to come across showing you the low voltage. Secondary control voltage is 27.2 volts. I have this black wire coming down from my light bulb, and it is wire nutted off to this white wire here, which, plugging this into the extension cord, I'll be able to provide a neutral. I'm going to go ahead and show you before I do that if I stick one lead inside my extension cord, I can now read 120 volts of power. Okay, and so I'm going to go ahead and plug in my neutral, and we're going to test that theory of closed circuit by coming up here to my common terminal, and you can see I read that 120 on each leg, and the reason why is because neutral is coming all the way to the base of this light fixture through the bulb, the filament, because the filament is not open, and then out over to here. And because this is on the normally closed, then here and here on this terminal, it's the same. So basically I can read neutral up here. So I go to show you when I put power here, the light will come on. We talk a lot about path of electricity. Very important to understand that path so you don't cross paths and have anything happen that's unfortunate on the job site, especially when it involves someone's safety. So we have to wire the high voltage and the low voltage part of this board. The only thing I have to do up here for M2 and M1 is just park the 2 out of the 3 speeds that I'm not going to use. I'm going to go ahead and do that now, because if I don't, then there's nothing safe about this, because the moment I have power here, which I'll go ahead and demonstrate now, I'm going to go ahead and just put line voltage here. And now we have 120 volts sitting on this wire. Now that 120 volts is running across my windings on my motor, and it's putting it out on medium, black, high speed, and red, low speed. And to show you that there's power there, see how my light comes on every time I touch the terminal with a different speed. And so I'm going to go ahead and disconnect power here for safety. And you know, Goodman, Amana, ICM, you know, they all put together these park terminals for you to be able to find the next speed if you wanted to hook it up. And if you're not using it, instead of letting them just dangle like we've done in other videos, we can actually now park them on M2 and on M1. So I like to use medium speed because I get 400 CFMs per ton. And so I'm going to take my low speed, which is less than that, and my high speed, which is more than that, and I'm going to go ahead and just sit these on their park terminals. So we'll go ahead and just push those on there, and then those will be out of our way. We won't have to worry about those now. Okay? So now it's pretty simple. I need to put a leg of power here and a leg of power here. Well, my medium speed, I'm going to break that across my relay. So I already demonstrated this is my normally closed portion of the relay. So I'm going to go ahead and wire my medium speed tap over to the normally open. I'm going to go ahead and push that on there. And I'm dealing with live power if I were to hook everything up, so that's why I don't have any alligator clips coming up here right now, because the last thing I want to do is hurt myself. So right now it's safe for me to do all this because there's no line voltage present just yet. So we want to go ahead and get all these wires out the way. And this is how you should wire yours up too. Okay, so we have high speed parked, we have low speed parked. I have medium speed hooked up. Obviously, you're not going to probably wire a light bulb, but if we were doing any kind of building automation, we could. However, I'm just putting this there so you can keep in mind that there's always power on that terminal when nothing's happening, and we'll know that because we'll have a light. All right, so the only thing I have to do now is just wire up my white wire to line and my common over here to line. That's going to be two different legs. My capacitor is already wired up. Okay, let's go ahead and finish up our high voltage. I'm going to go ahead and push one more terminal on here. I got a float switch here. I've got two ends. Both of them have a connector on them. I'm going to just go ahead and put one of these on my board now. That way everything else is just an alligator clip. I'm going to go ahead and move this out of the way so I can show you here. And if you look over here on the top left-hand side, we have a picture of the board again so we can actually talk about each terminal as we go down. On the top left, I have my transformer power in. And then I have, underneath that, I have 24 volts primary coming out. And then underneath that, I have my transformer common, which is obviously out, going back to the transformer. And then I have another common. If I wanted to use that, like say I'm running to my thermostat, then or if I need to have a common for my heater relay for my heat strips, I would wire that to here. And they're just trying to give you enough terminals so you don't sit there and use a bunch of wire nuts. It's easier to diagnose things if you can get your leads in there versus taking a bunch of wire nuts off. Down here we have G. This will be my fan call. Okay, that G is not ground. That is a fan call. And then the one next to it, it says speed up, which I'll demonstrate how that works. All right, so I'm going to go ahead and wire my float switch to the second terminal down on the top left, okay? And that will just say R, and that's an R output. And theoretically, I would wire this other side of my float switch to whatever's going to my thermostat. Okay, so I can break power to my T-stat in the event my float switch tripped. We've just put this here so we can give it a fault and you can see what happens. Okay, so all the wires that I have with connectors are all landed. At this point, we can just simply just take a bunch of alligator clips and start, dizzying this up. And I'm doing this way just for safety. When I get to the smart board and I'll wire it up, I will wire it up in a different order. Typically, I always try to work with high voltage and then I go down to low voltage. So we're kind of in the same order that we would normally go in. I'm going to go ahead and take 24 volt primary. I'm going to run that to R down on my transformer. So we have 24 volts going into the board. And then coming out of the board, we're already coming across the float switch. So right now we would have 24 volts right here. Now we need to put common on the board. So I have XFMR common, which is right below where I hooked my float switch up to. I'm going to go ahead and just put an alligator clip here. And I'm using green for my common. And so I'm going to run that down to common here. Okay. And at this point in time, our low voltage is theoretically complete. I could take this and wire this to this bottom terminal, because theoretically, that's all I would have to do. And you know what? Maybe I'll do that. Maybe I won't. We'll see. Let me go ahead and wire up some high voltage now. We're going to go ahead and take one load. We're going to go ahead and wire it. One leg of power. We're going to wire it up to one of my legs on the motor. We're going to come up with the other leg to the relay on the board. And you're going to see that the light's going to come on because it's normally closed on that terminal. Okay. And then once I get a G call, the light will go off and the motor will run. That's all we're missing right now is the G call. So giving it a G call, I told you that I can theoretically just put 24 volts on the G call from my float switch. I'll go ahead and just push this on here for now. In about 7 seconds, the motor will come on. So there will be a 7-second countdown. And that motor will run. And as you can see, the light went off. The motor came on. And, if I were to, have any type of power interruption here, I'm just going to turn my float switch upside down. This will break that G call. And there is a time delay on off. Now there's a 7-second time delay on, right? But there's a 65 to 80 second time delay on the off cycle. So once we hit that 65 to 70 seconds, 75 seconds, then the motor will shut off. You'll see the light come on because, as I said, there's always going to be power on that terminal when the relay's in the open position, because this is on the normally closed side. And this is a long time to wait when you're just looking at it. So we always recommend get a timer out, and even if it's been running for a while, just so you can confirm, hey, listen, this thing has been running too long. I've got my stopwatch out. It's been 5 minutes. If that's the case, then your relay is stuck in the closed position, which it does happen on these boards, and you just replace the board if that happens. If you have a customer, or if you're DIY and you're wanting to, not have that delay, there is another way of doing this. I'm going to go ahead and just hold this up just so I can break the G-call. I'm going to come over and I'm going to wire as carefully as I can. I'm actually going to short out between G on the board to my speed up. Excuse me. And when I do that, I'm going to get rid of that time delay. And so now, say I cleared out my drain line's good to go. There is no delay. It's immediately on. And when I lose that G call, it's immediately off. And so if you had a situation to where you didn't want that delay, you just wanted that blower to turn right off when the compressor shuts down, then you just simply short out between G and speed up, and there will be no delay. So we'll try that again. On, off, on, off. Now I'm going to go ahead and take the short circuit out, right? So now we're not shorting out between G and speed up. And at this point in time, I'll show you with my stopwatch. Let's see here. I'm going to go ahead and turn it over, and you'll see there's a 7-second on delay. Okay, and then there is a, I believe it's a 65 second off delay. We've been getting a lot of consistency with this board. So we're going to go ahead and flip it over, and I'm going to hit start on the timer at the same time. And this float switch was the easiest way to break my G call and hold my stopwatch at the same time. So, and also show you this is pretty much what happens when your float switch would trip. I would wire it coming out of R on the board, and then out to the float switch. Out of the float switch, then I would wire to my thermostat. Now the thermostat gives a G call. That's why I'm hooking my float switch back up to the board, because in that theory I don't have a thermostat here. On the smart board I'll show you, but on the smart board I'm not going to have a float switch on it. We will have more videos on low voltage components and electrical shorts and tips and tricks on how to get through those, so you want to stay tuned and make sure you're subscribing to this channel as we release more content, so you're getting that content. Also share this content. Very important to share this content. It's our job to help others, so if you know something that helps, share it with others. This video is one way to do that. And so that was about 65 seconds. And once again, if I were to short out between G and speed up, you'll notice that there is absolutely no time delay. So I'm going to go ahead and carefully get my alligator clip back there, and we're going to jump this out. There we go. So now that's shorted out. And once I give it a G call by flipping this over, it's instant. And once I lose my G call, it's instant. So let's look at another way we can do this. I'm going to go ahead and put this back in here. Let's just, excuse me. Let's say my fuse was open. Say my fuse was blown. Okay, I can just simply take my fuse out. Same thing. Now, anytime you have a blown fuse, you're not going to have, you'll have 24 volts going into the board, but you will not have 24 volts coming out on the R terminal. Okay, you'll have 24 volts going into your board, but if your fuse is blown, it's open, and if it's open, then you will not have 24 volts back out on R. So I'm going to go ahead and close this. I know I don't have any shorts here, so it's safe for me to do this, but never bypass your fuse. Your fuse is blown. Your fuse is blown for a reason. I just want to show you that if I were to short these out, okay? Then I have 24 volts now on my R coming out through my float switch, out of my float switch, theoretically, into my thermostat, out of my thermostat, over to G, and because G is shorted out, there's no time delay. Now, if I lose 24 volts, everything shuts off. So this would represent an open fuse. This had a 3 amp fuse in it. A lot of these fuses are color coded and they have the number 3 on it. That means 3 amps. Don't put a 7.5 amp because AutoZone or Discount Auto Parts or your local Walmart or maybe the auto section of any store, O'Reilly's or whatnot, not trying to give everybody credit, but all businesses do deserve it. I just want to make sure you understand that just because the fuse fits, it doesn't mean that it's the right size. So we want to make sure that these transformers are protected, and if we're going outside of those limitations of the transformer, either because we have a bad coil on a relay or there's resistance to ground or common or whatnot on a wire, if that fuse pops, we want to make sure that we trace that short down, fix the short, and then put the right size fuse back in there. Now, this does take a little bit of experience from a technician, so it's always best to make sure that somebody experienced is taking this project on. But don't take out that 3 amp fuse and replace it with a 7.5, a 10, a 15, a 20 just because it fits in there. If it's a 3 amp fuse and it blows, put another one back in there. If the fuse keeps blowing, the last thing you want to do is bypass it, because then you're going to blow your transformer. And then that's not good. You're just creating more work. It's going to be a bigger headache. So make sure that, when you're getting further into the sophistication of heating and air conditioning, qualified individuals are looking at this stuff. So, somebody with the experience is going to sit there and go, hey, there's a short, we need to fix that. We're not just going to bypass your fuse. All right, so we're going to go ahead and plug this back in. I'm going to go ahead and break red here so nothing happens while I do this. Of course it did that, why not? I should have a good enough connection now. Now, I like the time delay, so we're going to remove this short circuit, that jumper, and we'll go ahead and enjoy our off delay. Get all of our efficiency out of that evaporator coil. Now, if I wanted to change speeds to a higher speed, I would just simply remove my medium speed, remove my high speed. We can go ahead and do that real quick. I'm going to go ahead and probably want to wait for my motor to shut off, just so I don't have wires arcing because there's ampacity, because there's that current. So I'm going to go ahead and wait for my very long, annoying 60 seconds to time out. Should be real soon here. Here we go. So now I'm going to go ahead and just drop out power. So now I don't have any high voltage sitting up here on my board. And now I can swap these speeds around. I'm going to go ahead and put my safety switch back in there. I'm going to go ahead and remove my medium speed. Okay. I'm going to take my high speed off of M2, which has just been sitting there. I'm going to move this down to my normally open terminal. Hopefully that's a good connection. This is temporary, so I can leave it like that. And I'm going to take my medium speed, instead of leaving it hanging down there, I'm just going to put it back on M2, which is a park terminal. We should have a good enough connection here. Let's go ahead and just push it on a little bit more. There we go. I felt that. That's a much better connection. And now we're going to go ahead and wire it back up. Once I connect up here, you'll see the light come back on. I'm sorry, the motor came on. Why did our motor come on? I don't believe our relay was done, so we're going to go ahead and hook this back up. Let's see what happens here. Oh, the reason why is we have our float switch closed. So let's open that up. And I don't want to wait on my timer, so here's what I'm going to do. I'm going to go ahead and connect it back up to G and speed up. And now I'm going to leave that call for G, and that'll drop that out without a delay. Now I'm not waiting and wasting your time for a whole minute now that we know what it does. I don't have to keep demonstrating that. All right, so we have medium speed and low speed hooked up to M2 and M1. They're not hooked up to any kind of circuitry. They're safe to park there. I hooked up high speed to my normally open relay. My light bulb's still hooked to my normally closed portion of my relay. And I knocked off my delay by jumping out G and speed up. And you can hear the higher acoustics. You can see that the motor's running on a higher speed. And that's pretty much that. There's no reason to demonstrate low speed. You can imagine what that would be like. But we are good to go. I'm going to take it over to the smart board now, and we're going to wire this up one wire at a time. Stay tuned. Okay, we're at smart board now. We're going to talk about the blower control board, the PCB, which is a printed circuit board. That's all that stands for. ICM also makes this. I believe it's 277. We've talked about this timeline extensively in other videos. We talk about the permanent split capacitor motor and the electronically communicating motor, and how we have lost components through the decades. How everything is just integrated into one component, the ECM, and how sometimes we have to go back down this timeline and integrate other components, two or three components, such as capacitors, relays. Today we're talking about, still on the PSC motor, capacitor, and a PCB board. You know, how do we take this board and wire it up to a standard motor, and why was this board important? What did it do for us? You know, what makes it so special? Why, if it fails, would it be beneficial for me to install another one? And we've covered in the past, you know, how you can just simply put a relay in to get the job done and get everybody up and running and help the team out. But what if we had to go back with another board? And as you can see here, I've got two boards. They are the same. This is also a PCB board. And basically, we were using these on ECMs, and we still are. Now, today we're not talking about the ECM portion of it. We're just talking about the PSC motor. But getting right into it, I've got the image of the board on the screen. We're going to wire all these terminals up. I have my light bulb here too. Why not? We're going to talk about the values that I'm going to read on voltage, whether it's 0 volts, 240 volts with given neutral. I can also read 120 between any leg and neutral. That's the reason why I put that there, so we could talk about 3 values. We have low voltage terminal block, the thermostat. I don't have a float switch here. I don't have heat strips here. I don't have even a W wire for heat. Our focuses on the fan motor, and the only terminals that I really need is the R, C, and G. I just put the Y and the O there just because I wanted to make everything at least a one stage. This is one stage heat, one stage cool. We have a run capacitor. We have both legs. As you can see, I've color coded the motor with red terminals and black terminals, as well as your L1 and L2. That does not mean that run and start windings have to be wired to L1 and your common winding has to be wired to L2. That's just to identify that run and start need to be on the same leg. Okay. And this image has been used on all the other videos as well that we put out there. And if you're following these videos, we want to make sure that it's easy to follow them, especially if you understand my style of teaching and how I wire this up, going from one part to the next. Getting right into it, we have an integrated fuse on the board. I went over that expressively on the CANTEX box and on the motor. That has to be on this board for it to work. We talked about in our other videos how we don't have a fuse integrated on our transformer. As you can see up there, there's no fuse. And if I did have a fuse, well, then I'd have two of them. That doesn't make a whole lot of sense. So once we were going to get into boards, these fuses were already going to be there, and I knew that. So we wanted to just kind of work our way to that point. When we talk about wiring these components up, we talk about safety. Your safety is paramount, and the well-being of the equipment as well. We want to make sure it's just as reliable when you're done as it needs to be, and that you create no additional work that needs to be done because something wasn't wired properly. Best way to practice this is not wiring one component at a time, but wiring one leg of power at a time. We're going to go ahead and start with L2 since it's the closest to my transformer. And I like to wire my transformer first just because that's what I've been doing on these smart boards lately. Not maybe how I would do it in the field, but for this purpose, I'm going to wire my transformer because it's like 2 inches away from L2. I'm going to come down. I'm going to land one leg of power. I'm not going to jump over here to L1. Because I want to finish L2. Where else does L2 need to go? Well, L2 needs to get over here. But before it gets over here to my motor, it needs to come over to the relay that's on the board. And if you see here, it's upside down. Okay, but this is common, normally open, normally closed. So what I'm going to do is I'm going to obviously wire to my normally open, because we've already demonstrated that normally closed will always have power between common and normally closed in this state. So if we wired our motor to this, the moment we give it power on run and start, the motor is never going to turn off. So we obviously aren't going to wire to our normally closed. What we're going to do is we're going to wire here to common, so when we get power, common will make normally open. So we're going to come over with L2 and we're going to wire common. Common will be an input, and then out of the normally open terminal, that'll be our output. Okay, we're going to wire this over to common. And now we can go ahead and just start labeling everything, checking things off. L2 is good on my transformer. L2 is good on my board. L2 is good coming out of my board. And I've got one leg of power on my motor. Step back, look at it. Okay, it looks like L2 is complete. L2 doesn't need to be anywhere else. And see, that's a much safer way than instead of bouncing between component to component, because if I'm going from component to component, then I might be going from L1 to L2, L1 to L2, and it's real easy to cross paths, because it's harder to inspect something like that, especially when you're working above your head in an air handler where you might be standing on a stool, but it's definitely probably going to be dark. It's going to be a cramped work area. You're going to have tools in your hand. With that being said, you know, wires are going to be dirty, wires are going to be covered in all kinds of growth and whatnot, depending on the environment. On top of that, there could have been other repairs made in that cabinet previously or in the past, and at the end of it, you know, you don't know what's been done, undone, and if you assume that colors mean something in the absence of what could be accurate, you could misland a wire and cause harm to yourself or harm to the equipment. But if you run one leg at a time, then you can verify each end where the supply of voltage is coming from and where it's landing, and it's harder to mess that up. And it doesn't take any longer. You're going to get done within the same amount of time. Now I'm going to come over here. Now my transformer on the high voltage side is complete. Okay, I'm going to come over here. I'm going to give my run winding a leg of power. Go ahead and label that. I'm going to give my start winding from my run capacitor a leg of power. I'm going to come out, land that on start, and as long as my capacitor is closed, as long as it's not open or shorted, then L1 will be present all the way through. And with this, my motor will be good to go. Now, at this present time, I'm not going to read L2 here, and I'm not going to read L2 here, because I'm open between common and normally open, which is for common on the motor. Now, so if I looked at this, path of electricity is taking run and start, and it's feeding L1 to this point. So I'm going to go ahead and erase a couple of values here so we can put some true values at this present time. At this present time, I'm not reading L2 anywhere but at my transformer and on common. So what we're doing is we're actually, if I'm L1 here and through the winding, then I'm L1 here and the same here, right? And so that means back here I'm also reading L1. So if that relay is open, I'm actually reading 2 legs of power. So those 3 values that I told you would read, that I would go over, I'm starting to go over them now. We're going to read the value of L2 plus L1, which is 2 different legs. And those 2 different legs read 2 different voltages. 120 plus 120 is 240. So I'm going to read 240 across these 2 points with my meter. And so I'm going to leave that there until those values change. Okay, where else does high voltage need to be wired to? That's it. Now, I don't have 3 speeds here, so I'm just going to assume this is medium speed or high speed or low speed, doesn't matter which one, but the other 2 would be parked on M2 and M1. So I'm going to go ahead and just pick a different color. I'm just going to say, we'll just pick, we'll pick purple. I'm going to say here and here are going to be parked terminals. So I'm going to write that in. I'm going to say these are going to be inputs. And we're just going to say one of these is like high speed and one of these is low speed. And I'm just going to write down here that this is medium speed. Okay, those are going to be parked, those other 2 speeds that we're not using. Okay, so we have to wire a low voltage up. And once we get low voltage down here, that's going to make a call for the fan to come on, and this relay will close and these values will change. So how we wired up the transformer to the terminal block over here and the thermostat and the other ones was different because we didn't have all these terminals on the board. But now that we have an integrated fuse, we're going to have to wire the secondary voltage, the control voltage, to the board. So we're going to go ahead and do that real quick. We're going to go ahead and take, we're going to go ahead and take 24 volts And as an input, we're going to land 24 volts on the XFMR-1, which is the very top left terminal on the blower control board. Okay, and this is going to be an input. Now we need to give it a common back to the transformer. So I'm going to come out of here with my common, okay, which is an output, okay, and we're going to come up and we're going to just go ahead and give it a path back to the transformer. And so now the board has 24 volts on it. It is a working load. It is a working load. So at all times it has to have 24 volts on it. Now, with the 24 volts here through the board, okay, I have 24 volts on this left-hand part of my fuse. All right, and as long as the fuse is closed, all right, as long as we don't have an open fuse here, then I'll have 24 volts here. And then out of this, 24 volts will be present right here on R. Okay? And so basically what I'm saying is, as long as our fuse is good, we'll have 24 volts as an output on R. So the first one is an input, the second one is an output, and that's what we're going to run up to our terminal block here. I'm going to go ahead and erase these lines here so we don't confuse anybody. Just rewind that if you need to. Okay, now we're going to take 24 volts out of our terminal block and we're going to run it into our thermostat, and then we're going to take common. Instead of going back to the transformer, we can just take common back to here or here. It does not matter. I'm going to take it back to the board. Why not? But first, I've got to make it to the air handler through my low voltage wire. And then at that point, I can come down here. And as you can see here, I'm drawing an arrow as an input because my path literally is from here back to here. Okay? And so everything on the bottom left-hand side, the left-hand side of the board is done. The next spot would be the bottom left-hand side, which is our G call. So we're going to go ahead and take our G call, and that G call coming from the thermostat. Okay, we're not worried about the Y call, we're not worried about the O call, we're not worried about any kind of W calls, just that G call. That G call should always be present when there's a call for heat or a call for cool. So we're going to take this G call and we're going to go ahead and run it down here to the bottom left-hand corner of our board. I'll go ahead and hold the board up and show you. Okay, right below that resistor, there's a terminal. And this will be an input. This will be the call for fan. Now there's a 7-second on delay. And so the moment I do this in 7 seconds, these other values, they will change. So we're going to go ahead and erase some of these arrows. We're going to erase that L1 over here. And what's going to happen is we're now going to have L2 all the way across the relay because it's going to close, and now L2 will be here. And that's basically how that's going to work. Now I told you that I would cover the efficiency on this. And so there's a 60-second off delay. The moment we lose G, I'm going to go ahead and just say we're going to lose G from the thermostat. So now G is no longer here, right? And at this point in time, because there's no longer a G here, there's a 60-second, 65-second countdown. So let's just say the unit comes on and cools once every 10 minutes. and then it shuts off for about, let's say, 10 minutes, and then it comes back on for 10 minutes. In 1 hour, it ran 3 times, right? 30 minutes. We don't care about the run time. We care about how many times did it turn off. Well, that's 3 times per hour. So if we did some quick math, let's find a color that we can use. We can just do some math up here. So we're going to say in a 24-hour span, okay, we would multiply that by 3 off cycles. If there was a 10-minute on, 10-minute off, 10-minute on, 10-minute off, 10-minute on, and a 10-minute off, then that's 3 cycles per hour in a 24-hour period for cooling. That means it is cycled off 3 times in 24 hours. So we can simply say, okay, that's 72 minutes. And how I get to 72 minutes is each one of these represents 1 minute. So if every hour is 3 minutes, it was running, trying to shut off. And in a 24-hour span, that was 72 minutes. And 72 minutes, if I wanted to see how long that is in 1 month, I would multiply that, because this represents 1 day. So this would represent 30 days. So this is hours, this is minutes, this is days, this is how many times. So 72, I'm not going to try to do this math, even though it's simple. I come up to 72 times 30, that's 2,160 minutes in 1 month. So if I want to know how many hours that was, I can just divide that by 60 minutes, and I come up to 36 hours. So now, 36 hours. Your compressor shut off and left the blower running by design, because we lost the G call, we lost that Y and O call right on that heat pump, or that Y call on that straight cool. But this stayed in circuit for 1 extra minute. 3 times an hour, that's 3 minutes an hour, 24 hours. That's 72 minutes a day over 30 days, which is 1 month. Comes up to 2,100 something minutes. Divide that over 60 minutes an hour, and it comes up to 36 hours in 1 month. That your evaporator coil was either warm, if it was a winter time, or it was cold in the summertime for cool mode. You had the amp draw of just the fan motor, transferring heat still and humidity out of the air for 36 hours in a month without a compressor running. So you have to understand that that off delay is important. And now you can get rid of it. We'll talk about that. But it's very important, because 36 hours, I can't say it's free air conditioning, because it's not free to run a blower motor. But when you're talking about a compressor and a condenser fan motor that's probably running around 15, 16 amps, 12 to 16 amps, in conjunction with the blower motor that's running another 1.5 to 2 amps, okay, you're totaling between 14 to 18 amps of electricity to transfer heat. And now you're transferring heat for 2 amps of electricity over 36 hours. That is the efficiency that they're talking about. So it's not just the comfort that it gives you, it is the efficiency. And so that's very neat. And anything past that minute, basically, the coil is almost at a room temperature at that point. But because the temperature of that coil is either warmer or colder, depending on which mode it's in, okay, then the air moving across it, you are still transferring heat. Okay, now the heat's not being transferred to the outside unit, okay, or vice versa, but it is collecting on a warm surface to the air, or from the warm air, warm moist air if you're in Florida, to a cold coil, which will condensate. And so you're getting dehumidification on that back end. So this is way better than a relay. To stock it, to utilize it in the event that you had to take an ECM module out that naturally has that off delay and go back to a PSC motor like this, it'd be really neat to integrate this. Or maybe one of the other relays that we talked about that has some type of time sequence on an off delay. And that is the simple, probably the simplest version I can give you, just showing you with some transparency on some simple math on how it is efficient. Because when you first think about it, like, how is that efficient? Well, it's very efficient when you start looking at, well, 36 hours, and that's just 1 month. Okay? That's just 1 month. And this is when you start getting into bigger things, commercial, industrial. You start getting into dual circuits and compressor banks and lead and lag. And you start getting into, you know, condenser fan motors that don't all run at one time, and they don't need to if you can maintain the proper head pressure. You know, all that thinking is all about trying to be conservative and save energy. So you're not just, you know, moving more air than you need to, or moving more BTUs at a faster rate. It's not just about the well-being of the structure so we don't short cycle and harm the equipment. It's also taken in the concept of, can we save energy too? Can we get more comfort out of that product? There's a lot that goes into heating and air conditioning. There is a lot. And so it's not just about 24 volts and am I reading 240 or am I reading 0? There's a lot more to it than that. You need to understand the manufacturer's intentions and what they mean. And if you have questions, don't simply ask people, but simply read about it. Look it up. Ascertain what you're watching, even if it's on YouTube. There's a lot of good channels out there. There's a lot of people out there that are trying to put out content that's very helpful. Subscribe to this one so you can continue to get more content. At this present time, because it's been more than 60 seconds that I've explained this, the values that we will read will be L1 here. I'm not going to write it down, and L1 here. If I wanted to wire my normally closed up to my light bulb, in case you're wondering, I'm going to go ahead and do that. I would simply come out of here, which will be L2, and I would wire that to my light. And so in this event, the light comes on. But the moment that I get a G call, excuse me, that color didn't work out. The moment I get a G call from my thermostat and I get a G call to my board, okay, then I'm not going to have L2 present on my light, because L2 would be present here. But that's where I would wire that up. Is there anything else that we need to cover? Let's look. Yes, the speed up. We talked about the benefit of that off delay. All right, let's just say your customer says, I don't want it. I don't want it. I don't care. Shut that thing off. I just don't want it. Or maybe you just need to test your board out. Then simply I would have to short these two terminals. I'm going to use red. I would short these two terminals. Okay? And if I did that, then there would be absolutely no delay when it comes on, and there would be absolutely no delay when it shuts off. And that's your prerogative. Some customers do not like it. It's their equipment, it's their unit, it's your job to know what it's for, and you know how to utilize this. It's not good to have a bunch of wires hanging out that have voltage on it. I've demonstrated many times in all these videos where there's always power present and how you want to safe it off with a wire nut, or if there is a connection on it, go ahead and park it on M2 and M1. Plus it makes it easier if somebody needed to make a change, they can find those terminals and they can switch things around. I think that's going to wrap it up for this video. I'm going to leave off on the note that I always do. It's our job to share knowledge. That's why I'm in front of you, helping you out. Help the next person out. Share this video. There's a share button. Like the video. That supports the algorithm so we can easily be found. Please subscribe to the channel for more videos. There's a lot we got to cover. We can go on forever, and we plan on that. So please subscribe. You know, help your team out by, you know, sharing it to them as well. Maybe your service meetings. Hey, I found somebody that can probably help us out. He teaches different applications. Leave a comment in the box. I read those. You know, one of the reasons why we hurried up and got to this board was because of a comment in a box that somebody left that simply said, hey, what about Goodman boards? You're going to do that? Yeah, we are. It wasn't in the order that we wanted to do it, but we did kind of throw it out there as fast as we could. Can't always guarantee that I'm going to go over a subject that you want me to go over if we're not ready to talk about that. There's a lot we want to talk about governing parts of our trade before we just jump right into what should refrigerant pressures be and whatnot. But stay tuned, because those videos will come out. We'll talk about superheat. We'll talk about subcool. We're going to talk about coils that flood out with liquid, coils that are starved with refrigerant, properly charging, improperly charging, how that affects your compressor and that oil loss and that oil that should not be migrating. But if it does, where does it accumulate and what do you do? And what happens if, you know, I have a low voltage short, and how do I get through that call without going through so many fuses? And what about that zone board? How many CFM should I get in the bedroom? There's so many things that we can talk about. So please stay tuned. We appreciate all your support, and thank you for watching.